This is for 11 methods where you look at exercise 5D. I'm just going to go through the exercise with you. Okay, so exercise 5D is all about one-to-one functions. Okay, so we learned in exercise 5B or 5C that all functions must pass the vertical line test. So if I had a graph that looks like this, we know that it passes the vertical line test because no matter where I draw the vertical line, it only crosses the graph once. So that tells me that for every x value, there's one unique y value. Now, we're going to go one step further. If we want a one-to-one function, it must pass something called the horizontal line test. So if I draw the same graph of a correct, what happens is that it may pass the vertical line test, but if I draw a horizontal line, what happens? You can see it crosses the graph twice at some point. Okay, so this graph will not be a one-to-one function because it fails the horizontal line test. Okay, so for a function to be one-to-one, it must pass both the vertical and horizontal line test. Okay, for it to be one-to-one. Now, what the horizontal line test actually means is that it has one unique x value for every y value. Okay, so if you have two coordinates, let's just say the graph is just a bunch of points. If I have two coordinates, that have the same y value but different x values, that's not a one-to-one function because I don't have a unique x value for the y value because the y value is 4, but as you can see, it can equal 2 or 1 for the x, so that's not a one-to-one. Whereas something like, we'll go for an example. So the question is, which of the following is one-to-one? If you look carefully at the y values, okay, so we already know their functions. Okay, so we don't need to think about look at the x. We don't need to do the test for function. We just want to check whether each y value has a unique x value. Okay, so as you can see, these both have a 4 there. Okay, now the problem is there's different x values. Okay, if there's different x values per y value, then it's not a one-to-one function. So not one-to-one. It's still a function, but it's not one-to-one. Part B. These all have unique y values and unique x values. That's one-to-one. So it is one-to-one. So tick one-to-one. Now, in the book, we've got graphs, and we want to check whether they're one-to-one. No, it's just not one-to-one. Okay, because it passes the vertical line test, but it doesn't pass the horizontal line test because it crosses twice. Okay, so we call this function many to one because there's many x values per y value, many to one. Okay, many to one. Now, this is going to be one-to-one because no matter where I draw the horizontal or vertical line, it's only going to cross the graph once, so it's one-to-one. This is, it passes the vertical line test, but if I draw a horizontal line, we have a problem because it crosses indefinitely, okay? So this is, again, many to one. It is a function because it passes the vertical line test, but it's many to one. This one is one-to-one, yep. And this one is many to one. Now, the book doesn't go to explain many to one, but I would like you to learn it. So when it crosses the horizontal line twice, it's many to one. Okay. Now, you might get a question asking you this, like what is this? If I draw a vertical line, it fails it because it's not a function, and if I draw a horizontal line, it doesn't pass that either. So it's a relation. And it's a many to many relation. Many to many relation. So it's a many to many relation. Okay, so just so I'm getting used to the terminology. So another example, if I have a parabola side, okay, it fails the vertical line test, but passes the horizontal line test. So this would be called a one to many relation. So hopefully that gives you an idea of how to define relations and functions. Okay, so it fails the horizontal line test. So there's for every x value, there's two y values, and for every y value, there's one x value. Okay, so hopefully it gives you an idea of how to define these. Now let's look at implied maximal domains. We did go through this briefly in exercise 5. C. So the implied domain is the natural domain the graph occupies. Okay, I think we went through this at 5A actually. So there are easy ways to determine the implied domain of a graph without having to sketch it. Okay, so if you don't have to sketch it, don't. Okay, and if you're forced to, then by all means do so. So you can simply by look at the restrictions placed on the graph mathematically. And what do I mean by that? Restrictions could be a square root or a fraction in the function. Okay, so for example, if I have y equals root x, what's the natural restriction? Well, the square root itself is a restriction because what do we know about what can be inside a square root? Well, we know that whatever's inside, it cannot be negative overall. So we know that a natural restriction would be x has to be greater or equal to 0. Okay, it can be 0. You can have the square root of 0, but you can't have the square root of anything negative. So this will be your natural domain because it's the restriction itself. Similarly, if I had y equals 1 over x, what's the natural restriction? Well, I know that the denominator cannot equal 0, so x cannot equal 0, so that's the domain. Okay. If you want to write that as a interval notation, that would be reals, real positives, union 0, because it's reals including 0. And the way to write that is reals excluding 0. Now, the book might write like this, or it might write like that. The book might write it like this or like that. Okay, so it's really important that you just look at the restrictions in place. So if I had a graph of y equals x squared, there's no restrictions on it. So the domain is all reals. Okay, so the domain will be all reals for this. Okay. Similarly, if I had a linear, I don't have any restrictions on it. So domain would be all reals. Okay. So there's an easy way to just looking at the graph what the natural domain is. So let's do some examples. For A, I can see that there's a square root there, right? Remember I said whatever's inside the square root cannot never be a negative number. So I need to make sure that 2x minus 5 has to be greater than or equal to 0. So let's solve it. 2x is greater than or equal to 5. X is greater than or equal to 5 over 2. Okay, so that's your domain. So if you write an interval notation, this will be 5 over 2 to infinity. B, as we can see, the denominator can never be equal to 0. Okay, so if it equals 0, then that graph doesn't work. So let's find when that happens. So if you try to find when that happens, let's just set that to equal 0 because we want to find when, for what x value, it leads to that equaling 0. So I'm going to solve it. So x equals 5 over 2. So the domain would be x cannot equal 5 over 2 or reals except 5 over 2. Okay, so it's as simple as that. You're simply looking at the natural restrictions of a graph. So for question 3a, we want to find the implied domain. So the implied domain would be reals. Okay, the implied domain here would be, again, look at the restriction. That has to be greater than or equal to 0. So x has to be greater than or equal to 0. Okay, this will be all reals. For this one, we got 9 minus x squared has to be greater than or equal to 0. Okay, now I need to factorize this. So we've got 3 minus x, 3 plus x greater than or equal to 0. You're going to draw a graph. It's going to be a frown. You've got negative 3 and 3. So when is the graph greater than or equal to 0? When x is between, so you want this region, x is between -3 but less than 3. Okay, so x is between -3 and 3. This one, the root x, well, first of all, we have a square root, so x has to be greater than 0, plus also, because it's at the bottom, x cannot equal 0. Okay, so 1 on, that can't, we need to find when root x is equal to 0, so x equals 0 in this case. So we don't want x to be equal to 0, okay? So can you see we've got two conditions here? How do I combine conditions? How do I reconcile these two conditions? I know that x can equal 0, but x has to be greater than or equal to 0. So meaning that if I want to combine them together, x has to be greater than 0. That's the result, because it cannot equal 0. Okay? For f, that's just a normal quadratic. The domain is reals. Okay. Now to get the range, well, the range is reals for linear. To get the range, we know that the range for B would be, well, it's a root graph, so you can't really do the range without drawing it. So we have to bite the bullet and actually draw these. So 2 root x, the range for that would be real positives including 0. So you could write y is greater than or equal to 0, or real positives including 0. Okay, the range for this would be reals. The range for this would be, well, this is actually a semicircle. It's the bottom half of a semicircle. Now I know the bottom half of the semicircle, I already know what it looks like. It's going to look like this. It's going to look like this, and there'll be -3, there'll be -3, 3. So the range would be between -3 to 0. Okay, that'll be the range. For E, the range would be, now that's a 1 on root x graph. Okay, so there are, x has to be greater than or equal to 0, so the range would be, well, we haven't really covered this type of graph yet, and that's okay. We just know that y will always be positive. Okay, so logically, because x cannot be greater, it cannot be a number that's 0 or negative, it means y is always going to be a positive number, and there's no restrictions on the y, so y would always be from 0 to infinity. Okay, for f, it's going to be reals. Okay, all reals. Now let's look at the entire domain range of these. Okay, so as you can see, we've got a square root, so x minus 4 has to be greater or equal to 0, so x has to be greater or equal to 4, that's the domain. Okay, or you can write it in interval notation, so that'll be 4 to infinity. For this one, 4 minus x is greater or equal to 0, so x has to be less than or equal to 4. Okay, this one, again, we're just looking at the restriction. We don't care about 2 or the 3. Okay, whatever mathematical restrictions are. So x minus 2 is greater than or equal to 0, so x has to be greater than or equal to 2. This one, x minus 4 cannot equal 0. Okay, so x cannot equal to 4. Okay, so that's the domain. That's the domain. Okay. Now to get the range, we do have to sketch it, the graph. So x minus 4, so the root graph has moved 4 to the right. So the range would be from 0 to infinity. Okay, or real positives union with 0. Okay. The second one. Now you have to actually take the negative out. So this will come x minus 4, so it's moved 4 to the side, and then it's a reflection. So this is the domain, but the range would be, again, 0 to infinity. Okay. For C, the graph has moved 2 to the right and 3 up, and it's going to have the shape. So the range would be, this would be 2, 3. The range would be 3 to infinity, including. Okay. For D, um, well, it hasn't moved up or down, so the range would be just the asymptote still at y equals 0. So the range would just be reals excluding 0. Okay. So when finding the implied domain, that's pretty straightforward. You don't need to draw the graph, but when you get to the range, you actually sort of need to visualize what the graph actually looks like. Okay, and I encourage everyone to practice visualizing because it will make a big difference in your understanding. Okay. So next part, the graph is shown of the relation. Okay, so we've got y squared equals minus x plus 2. We want to form two functions with the domain 0, negative infinity to 2. Okay. So what it's basically asking you to do is to break the graph into two graphs. So one graph here, one graph there. Okay. Now this is a parabola on side, so we're expecting if I square root this, I get plus or minus square root of negative x plus 2. Okay. So we've got two functions and we want to specify the range of each. Okay. So very simple. Form two functions. So I want to put this in function notation. So remember the function notation, fully defined function notation is f such that I'm going to call my first function f. I'm going to use the positive version of it. So f such that the domain is negative infinity to 2 mapped into reals, and I write the rule. So f of x is given by negative x plus 2. Okay. I'm going to call my second function g. It's also from negative infinity to 2 mapped into reals. G of x equals negative x plus 2. Okay. What is the range of each? So range ran of f, ran of g. The range of f would be the top half, which means that it is 0 to infinity, because it goes on forever up there. Okay, 0 to infinity. The range of g is negative infinity to 0. Okay, so revise your function notation. We went through this in 5C. Okay, I know this is new for you, but you got to remember the format. Okay, so once you do that, this should be pretty straightforward. Okay, and obviously understanding the notation. I know this is a lot to take in sometimes. That's okay. Question 8. We want to draw the graph. So this is in fully defined function notation. So it's a f. We've got a function f such that the domain is reals. Okay, mapped into reals. The rule of the function is a quadratic. So f of x equals x squared minus 2x plus 4. By restricting the domain, form two one-to-one functions that have the same rule as f. Okay. So before we do that, we need to find out what the function looks like. Okay, we need to sketch it. So we've got f of x equals x squared minus 2x plus 4. The y, so if you want to write like this, the y-intercept, it's really the f of x intercept, but we'll call it the y-intercept just for convenience, is at 0, 4. The shape is a smiley face. The turning point, I'll get this into scaffold form. So this will be x minus 1 squared minus 1 plus 4. So x minus 1 squared plus 3. So TP is at 1, 3. So if I sketch it, the graph's going to look like this. So we have a TP at 1, 3 and intercept at 4. Okay. And you draw, instead of y, you write f of x here. X. Okay. Which makes sense because that's like your new y. That's your new label. Okay, we want to form two one-to-one functions that have the same rule as f. Okay, so I can have this part and this part. Okay, so I split the graph into two parts. Now I can then define it. So f such that it's no longer, the domain's no longer real. So for this part, the domain is negative infinity to 1 mapped into reals with the rule f of x equals, it's the same rule, except I've just restricted domain to only the first half. I'll label the second function g, goes from 1 to 1, including 1, to positive infinity, reals g of x equals x squared minus 2x plus 4. Okay, so that's basically how you do these questions. Now, the reason why I split it in half that way is because if I have a function that looks like this, that's one-to-one, because I do horizontal line test, it passes. Vertical line test, it passes. Similarly, when I split the other way around, it passes both the horizontal and the vertical line test. That's why I don't split it, somewhere up here. And that's why, I don't split it like this. I don't split it like this because that fails the horizontal line test. So I have to split it right in the middle for the quadratic. So hopefully that gives you an idea of how to approach exercise 5D. I mean, you probably have a lot of questions. Please don't be shy to ask. Okay, just post them up on Google Plus. I'm more than happy to go through any specific questions you have on this exercise.